Hello, students. Welcome to my first attempt at teaching statistics online and remotely. As I have this set up, I believe I have everything I need. You should be able to see both. You should be able to see my face. You should be able to see my screen. You should be able to see or to hear my voice. And I have my coffee right here. So I'm hoping that we can get through this. Now, I have planned a shorter PowerPoint for a variety of reasons today. One, I want to go through it at generally a pace that is going to allow you to really pick up what is happening here. Since this is not live, feel free to pause it at any moment if you need to go backwards or kind of process the hand calculations at your own pace. That's stuff that now becomes possible. So, think optimistically about what's going on here. I'm going to start my PowerPoint presentation, move this a little bit out of the way. And you will see that today we are covering a two means t-test. I'm recording this on a Sunday afternoon in my office. Certain lectures will be recorded from my apartment at home, but this one is going to be done right here in the office where I knew I could be on campus Wi-Fi and resources and all that stuff. I'm going to try a new gimmick or a new gag to get started since I don't have the chance to see you guys really at all the rest of the way. With all the live sports canceled and really nothing on television, I'm rewatching a lot of old movies that I used to like or still do like. And so I want to start each lesson with just a completely random comment I thought from rewatching old movies that I never really noticed before. And our first one is going to be about Top Gun, which remains an absolutely fantastic movie. It was on Friday night. I watched it while I was falling asleep. At the very end of Top Gun, Tom Cruise, right, Maverick, has this amazing mission. It's his first time, flying with the aces, and he overcomes his PTSD and shoots down a bunch of MiGs in the Indian Ocean, that hotbed of international tension, the Indian Ocean. And then when he comes back down, there's this huge celebration, and they tell him, hey, you're being given by the Navy your choice of duty, right? You can go anywhere you want. And he says, I think I want to be an instructor, which is a nice coming full circle moment. And then I was like, wait, you want to be a teacher? Dude, you just graduated flight school like 3 days ago. We literally saw the ceremony where you lost the Top Gun title to Iceman, and now all of a sudden you're just never going to really fly again. Never really sat right with me, or doesn't sit right with me kind of going forward. Anyway, in the interest of moving forward, let's talk about our two means t-test. So in the way of review, you will remember that we constructed the T formula to account for an alteration of a situation where we would use the Z formula. When we wanted to compare a sample mean to a population mean, and we knew what the population variance was, and by extension, we knew what the population standard deviation was, that was a situation where we could use the Z-test. If you see population SD or variance, that is a dead giveaway that you can use a Z-test. And that also allows you to make use of many of the things you know about the normal distribution. You were able to use these critical values of 1.96, 1.645, and 2.576. But then we encountered a new situation on Wednesday of last week, which was when we had to compare a sample mean to some type of predetermined value, even if it's a population value, when the population variance is not known. And it turns out that is usually more common than situations where we'll be able to use a Z-test. That necessitated the T distribution, okay? So that was what known as the one sample or the one means t-test. Just one mean compared to a value, and we were then able to use an estimated standard error, right? S of X bar instead of sigma X bar. And that's something that allowed us to still do generally the same things, but it was all constructed around this estimate of the population variance. Now, here's what we do today. Today, I want to compare two sample means, or I want to compare subgroups of the same sample. Now, here's why I might want to do that. let's just take one thing that is known to be important to sociologists, or something that sociologists generally are interested in researching. Let's take the wage gap, for example. Okay, so it's probably been brought up in many sociology classes. Also, if you've been a member of society, if you're planning on getting a job at any point in the near future, it's hard to get over the fact that that exists. So let's say I take a sample of males and determine a mean for their starting salary. And then I take a second sample of females and determine their starting salary. Now I have two sample means, one for males, one for females. I have two standard deviations, one for males, one for females. And most importantly, I have two theoretical populations, right? These samples are meant to stand in for the entire population of male workers and the entire population of female workers. So what I'm doing here is comparing two sample means to each other. Okay. Now, the necessary caveat here, you must have an interval level dependent variable. Let's start with that and break that down. Why do I have to have that? Well, if I'm comparing means to each other, I have to have a variable for which it is appropriate to calculate a mean in the first place. Without an interval variable, I don't have a mean. Without a mean, I don't have a t-test. Okay. So I have to be doing this with something like income, right? And in the wage gap example that I just used. And you must only have two groups that are being compared to one another. So males versus females on salary. If I wanted to compare the GPA of underclassmen to upperclassmen, right, just those two groups, that could be a t-test. If I wanted to compare the GPAs of anthropology majors to sociology majors, that would be a t-test. So it has to be two and only two groups. If I wanted to compare salary, let's just take the income thing again, and I wanted to compare that from whites and non-whites, right? Now that's granted, that's throwing everybody into a just one pool of analysis for anybody who isn't white, but still, like I think you get the point. Like statistically, that would be a t-test. Pardon me. So now, if our research design is changed, so too does our hypotheses. If we are hypothesizing any type of difference, then the null hypothesis will be that there is no difference between the groups. In contrast, H1, or my alternative hypothesis, that's the thing that I'm trying to show. I want to see that there is a difference between these two groups. That would be, there is a difference between the groups, or mu1, the mean of the first group, is not equal to mu2, the mean of the second group. So, repeat that. My null hypothesis is that mu1 equals mu2, and my alternate hypothesis is that mu1 does not equal mu of 2. This obviously would imply a two-tailed test. You will see the distribution listed or drawn at the bottom of my screen here. This is actually very common, these types of t-tests and differences in means. It's very common in biomedical research, clinical research, where you try to control, like, say, one group gets a treatment, the other group does not. That's called the control group. And you see, did they experience different things? Because if you keep everything else randomly assigned and you keep everything else constant, then any change in the outcome is likely to be due to the one intervention that you specifically controlled, okay? So this is what I'm looking for. In the situation you see down here where the treatment group mean is very different from the control group mean, that would likely be support for the alternate hypothesis. You can just look at this graph here and see that, yeah, the treatment group mean is in a different spot of the XY axis than the control group mean. It is different. Therefore, mu of 1 does not equal mu of 2. I'll stop there for a second if you guys want to write this down. Okay. Now, Of course, if we're changing the nature of the hypothesis test, we also have to change slightly the formula. Now, you'll remember a standard error is, on average, how much will a sample mean differ from the population mean? That's absolutely crucial here because A, we don't have the population information to go off of. We have to estimate it. But here we're actually estimating it twice. If you have two sample means, you have two populations. And if you have two populations, you now have to estimate two separate standard errors. So the t-test is going to draw upon this very issue. You're going to have to, actually, let me go back to the issue of the wage gap because I think that's very understandable here. If I personally wanted to see, is there a significant earnings difference between males and females in the United States? I have to get a sample mean for males and a sample mean for females. But then I also have to estimate the standard error for males. And independently of that, I must estimate the standard error for females. So we're really operating with two standard errors here. So if you open your stats packet, you will see the following formula underneath the subheading of two means t-test. Notice what I've written in red here. You will only use this formula if you are operating with two independent samples of an equivalent n. This only works if your n's are equal. Put another way, if I take a sample of 100 males and a sample of 100 females, great, use this formula. If I take a sample of 125 males and 100 females, I may not do this. There will be a workaround to that, and that's what we're going to do on Wednesday. So what you're seeing here on this formula, let me run through this. S of x bar 1 minus x bar 2. It's an estimate of the pooled difference between the standard errors of the two samples. That will be calculated by taking the square root of the variance of the first population divided by its sample size plus the variance of the second sample divided by its sample size. Now, functionally, if you're adding fractions to each other, this will become easy. This is a little bit easier because you are operating here under the assumption that n1 equals n2. Therefore, you essentially add the first variance to the second variance and then express it over that commonly held sample size. Why do I keep saying variance? Very important. This is a squared, this is a formula that needs the squared property. So see how it says s squared 1 and s squared 2 underneath the square root? That will be taken care of at a later point. But for now, we're going to always want to square our standard deviations if that's what's given to us. Otherwise, you will end up with the square root over the n, and we don't quite want that right now. So what this is doing, and I'll run through that one more time here, the square root of the variance over the first sample size plus the second variance over the second sample size, that is s of x bar 1 minus x bar 2. It is estimating the extent to which the observed difference between standard errors is deviating from the actual difference. Because now you're not just estimating the standard error of a population, you're estimating the difference between the male standard error and the female standard error. That's what s of x bar 1 minus x bar 2 is referring to. I'll stop there for a second, let you collect yourself, and then we'll move on. So then the t-test is going to unfold similarly with most of the additional labor actually happening right here with this estimate of the pooled standard error. So what we do is calculate s of x bar 1 minus x bar 2, and that goes in the denominator of the t formula, which is expressed as follows. X bar 1 minus x bar 2 over s of x bar 1 minus x bar 2. So we do, follow my cursor here, we do this formula on the left side of the screen first. We plot that into the denominator of the t formula and divide that into the difference between x bar 1 and x bar 2. In other words, as I write on my PowerPoint, we are subtracting the mean of the second sample from the mean of the first sample, and then we're dividing by this pooled estimate of the difference between the standard errors. Oops, let me go back here. So how do I know when to do this particular t formula? Well, if I lack the population standard deviation or variance, and I have two separate sample means, and those samples consist of the identical sample size, this is what I'm going to do. Now that's the formula. If you make a mistake, it's probably in the creation of S of x bar 1 minus x bar 2. That's where the most can go wrong. Because the t formula itself, once you have the information, is not terribly difficult. So why don't we try our hand at this? I've created an example. Let's say I want to know whether self-esteem among Ohio State students is significantly different from self-esteem among University of Michigan students. So here's the question. Is 3.75 significantly different from 3.65 at the 0.05 alpha? In other words, are these two sample means different with 95% confidence? So what I've done here is created a hypothetical scale in which students rate their self-esteem on a scale of 1 to 5, with 1 being the lowest and 5 being the highest level of self-esteem. In order to do this, I take a sample of 25 Ohio State students. I calculate a sample mean for those Ohio State students of 3.75. And I calculate a variance of 0.45. Please read that very carefully. Notice how it says S squared. That means it's the variance. Now on the other side, I go to that school up north and I take a sample of 25 Michigan Wolverines. And of those 25 Wolverines, I get a sample mean of 3.65. Not surprised it's a little bit lower. All those losing seasons probably takes a toll on you. And the variance here is 0.34. So my t-test formula we just ran through is going to tell us the probability that this observed difference is statistically significant. Because again, I know there's a difference here, but is it due to random chance? Is it just due to sampling error? Or is it likely to be expressing a real difference in the self-esteem levels of these two populations? Are we ready to get started? Let's do it. So step 1, we want to always state what we know. Write down the things that we know. So I know on the Ohio State side, or X1, sample mean is 3.75 and the standard deviation, or the variance is 0.45. I know that for University of Michigan students, the sample mean there, X bar 2, is 3.65. And the variance here is 0.34. And my N is 25 for both of these samples. So I have a cumulative sample size of 50, but not really. I don't want to lose track of how many belong to Ohio State and how many belong to Michigan, because once we get to a situation where the sample sizes are not accurate or are not equivalent, when the sample sizes are not equivalent, I'm not going to want to pool them in quite that way. I'm going to have to be a little bit more careful about that. There is no direction implied here. I'm just going to go back 1 second here. You are asked, is 3.75 significantly different from 3.65? Therefore, this is a two-tailed two means t-test. A two-tailed test, you will remember, does not seek to find a specific direction. It doesn't ask whether something is greater than or whether something is less than. It just asks for a difference. Therefore, if we find that x bar 1 does not equal x bar 2 with 95% confidence, we will be able to imply that mu 1, the population mean, does not equal mu 2, the second population mean. I really wish I could ask you guys if you have questions, but I'm sitting in my office like a dork right now, droning on into the computer. But we make the best of it. Why did I give you the variance here? Very simple. I'm a nice dude. I'm looking out for you. But if you ever read a word problem and you are given only the standard deviations of each sample, you already have the variance. You just don't know it yet. So if you are given standard deviations, all you have to do is square them, and voila, you have the variances, okay? So running through this formula one more time here, I will need to take the first variance over the first sample size plus the second variance over the second sample size. Then I take the square root of those of that addition equation, and that is my pooled estimate of the difference between the standard errors. So when you have homework to do not count on being given the variance. You're almost never given the variance. You're almost always given just the standard deviations, both of them. So when you see this formula of s squared p, understand it is instructing you to square your standard deviations. Okay? So step 2, let's go over our hypotheses. You'll remember it's a two-tailed t-test. Therefore, I'm just looking for a difference. So I would write this as follows. H0, self-esteem scores among Ohio State fans are similar to self-esteem scores among U of M fans. You could also write or say something like, self-esteem scores among Ohio State fans are not different from self-esteem scores among U of M fans. Or put another way, mu of OSU equals mu of UM. Then conversely, my alternate hypothesis, self-esteem scores among Ohio State fans are significantly different. Different, that's all I care about. Different in either direction, doesn't matter. I just need to find a difference from self-esteem scores among U of M fans. Or H1 equals mu of OSU does not equal mu of UM. So I'll repeat those. My null hypothesis, mu of OSU equals mu of UM. My alternate hypothesis, mu of OSU does not equal mu of U of M. Okay, I'm going to go forward in the interest of keeping this video shorter, but if you need to go through this again, don't hesitate to go backwards or to pause it, while you work this out on your in your notes. And as we go forward with the math, I strongly encourage you to be doing these things in your notes. Take your pen and actually make this happen in your notes, okay? Those students who do that will get the most out of these lectures. Okay, so step 3, set our alpha level. All this requires is remembering what the alpha level / confidence level is. So you were asked at the 0.05 alpha, you were asked with 95% confidence. Therefore, my alpha level is 0.05. Knowing that this is a 0.05 alpha level and knowing that this is a two-tailed test, we're going to have to go to our stats packet to the t-table. So pause this and get that out if you don't have it out yet. Determining the critical region will require a slight alteration to our degrees of freedom formula. Here, degrees of freedom will be expressed as n1 minus 1 plus n2 minus 1. Another way to think of this would be n1 plus n2 minus 2. Either way you run through that, and I see that my degrees of freedom is 48. Because the first sample size was 25, the second was 25, I subtract 1 from each of those samples. And I have to do that because keep in mind, I have 2 theoretical populations. Therefore, a degree of freedom must be subtracted from each one of my 2 samples. And I get a degrees of freedom of 48. Look this up, and the critical T is equal to plus or minus 2.021. Please run through your stats packet and find that. I look for 0.05 on a two-tailed test, and I run down until I get to my degrees of freedom. Now, you will notice as you're looking at this that we go from 29 to 30 to 40 to 60. So our degrees of freedom of 48 is not listed on this formula sheet anywhere. When it isn't, we round downward. So because 48 is less than 60, I have to round down to 40. And then I find the column for 0.05 at a two-tailed test, and I see right there for 40, 2.021. That is going to be my critical value. So when I run through my T formula, I will reject the null hypothesis if the T statistic that I calculate is either greater than positive 2.021 or less than negative 2.021. This is the boundaries of the critical region of that T distribution. I'm going to move on momentarily. Please pause it if you still need time to work through this. Okay, so our first 4 steps are taken care of without too much trouble. So now I have to calculate the T statistic. I must do x bar 1 minus x bar 2 divided by s of x bar 1 minus x bar 2, where the denominator of the T formula is the square root of the first variance over n plus the second variance over the second n. So I'm going to start with the equation on the right side here. Go back to your notes and try your hand at this. Grab s squared 1, grab s squared 2, and your equation will look something like this. I'll give you a moment to actually do the math on that. So pause it if you're not up to speed. The square root of 0.45 divided by 25 plus 0.34 divided by 25. Okay, and you should have an answer of 0.18. That's the denominator of the T formula, okay? So using the T formula then, I will construct the following equation based on my knowledge of the sample characteristics. 3.75 minus 3.65 divided by 0.18. 0.18. So using this formula here and the notations that you have in your notes, please try your hand at this. Okay, and running through the formula, we should have gotten 0.56. 3.75 minus 3.65 divided by 0.18 will give you 0.56. That's it. That is your observed t-statistic. So I ask you, is 0.56 greater than 2.021, or is it less than negative 2.021? And the answer there, clearly, it is absolutely not greater than 2.021 or less than negative 2.021. So this tells me what I have to do. Step 6, decide and conclude. We fail to reject the null hypothesis and conclude that self-esteem among U of M fans are not different than self-esteem scores among Ohio State fans. Really? I find that surprising. I would have thought all those losing seasons would have really taken a toll on the UM state of mind. But hey, that's what the numbers show. I fail to reject the null hypothesis. I cannot say with these two samples of 25 students each that the self-esteem scores are different. Right? Nothing more complicated than that. I'm going to run through this one last time here so we understand the steps here. I stated what I know. I saw that I have 2 sample means. I have 2 standard deviations / variances. I have 2 sample sizes. Even though they are exactly the same, I don't have a hypothesized direction. So I want to know, are self-esteem scores different or are they not different? Mu of 1 equals mu of 2 on the null. Mu of 1 does not equal mu of 2 on the alternate hypothesis. Third, I set my alpha level at 0.05. 4, I took my degrees of freedom of 48 to get the critical T of plus or minus 2.021. And then I calculated my t-statistic by first calculating the estimate of the difference between the standard errors, 0.18, and then I divided that into the difference between the 2 sample means, compared that to the critical statistic, and I determined that there is no difference between these two. Okay? So that's what I got for you. Please try to run through it if you got the wrong answer, right? And please feel free to rewatch certain segments of this, because when I come back, we'll be covering the t-test when the means are not equal, okay? I'll be reaching out to see how your viewership of this went. For now, I'll just say thank you very much for bearing with me in this completely bizarre format. Keep on working with me. We'll get through it all together. Thanks very much, and I'll see you in a couple days.